Welcome to the 24th International Conference of Computational and Mathematical Methods in Science and Engineering. My name is Carlos Molina, and in collaboration with Dr. Jorge Marcias and Dr. Armando Gallegos, we would like to present you our current work, numerical simulation of the fractional two equations Davey-Stewartson system via a conservative and an efficient scheme. Let me introduce first the Davey-Stewartson system. The Davey-Stewartson system is a system of two coupled nonlinear partial differential equations that is used to describe the evolution of a three-dimensional wave packet on water of finite depth. This system of equations was reformulated as the Generalized Davey-Stewartson System, which is a system of three coupled nonlinear partial differential equations that is also used to simulate wave propagation in an elastic medium with coupled stresses. The generalized Davey-Stewartson system looks as follows, where U represent the complex amplitude of the short transverse wave mode, W and V define the long longitudinal and long transverse wave modes respectively. Here we also see that there are some real constants that govern the behavior of the system, and they embody critical physical characteristics. These real constants are constrained by the following definition, and some of these parameters can have any sign, but we have the stipulation that gamma has to be different than 0. As a system of equations, we need initial and boundary conditions in order to be able to solve the partial differential equation. This ensures the well-posedness of the problem and also the physical relevance of the solutions. There are three properties of interest. The first one is the mass given by the density of probability, the energy given by the Hamiltonian of the system, and the momenta in the x and y directions. These three properties are of importance, and we want to demonstrate the conservation of these quantities in our current work. For this work, we are going to be presenting the fractional Davey-Stewartson system, and we are going to be analyzing it. First of all, let us explain a little bit about fractional calculus. Fractional calculus is an extension of traditional integer order calculus, and it involves real or complex order derivatives and integrals. This gives us the possibility to have a wider range to analyze the physical properties of a system using non-integer differentiation and integration. Fractional calculus gained importance in several fields such as fluid mechanics, physics, and even biology. For this work, we are going to use the Riesz functional derivative. We have the advantage here that we can use the inner product properties in order to complement the derivations that we are going to be using. So this is the importance of using the Riesz functional derivative. Here we can see the definition of this derivative functional, and we see also that this depends on the gamma function. The generalized Davey-Stewartson system will look as follows using fractional order integration. Now we are going to see that we have new variables for the integration orders. The parameters remain the same, they have to be real constants, but the order of the derivation will lie between 1 and 2. We also need the initial boundary conditions, so the order of the equation system remain the same. Now we can talk about the numerical implementation. First, we need the following definitions. We have to define the real number g, which is a function of the gamma function, and then we can define the fractional order centered difference of the function of order lambda. With these definitions, we have the following lemma, which is going to be allowing us to have the representation of the discrete fractional Laplacian, which is going to be used to discretize our equation. We also need the following setup for the discretization along the x and y axis and over time. Remembering that we are going to have regular partitions for the intervals on x and y and time beginning on 0 and ending on a finite time. For the operators and approximations, we have the following derivatives for the first order, for the x, y, and time. And we have also the following temporal average operator, which will provide quadratic order of consistency around the point xn, yn, tk plus 1/2. Motivated with these definitions, we can have the following difference operators that we are going to use on the discretization of the Davey-Stewartson system on the fractional version, which will look as follows. Here we can see that we have the fractional order derivation on the different directions and also the time operator. We still need the initial and boundary conditions, and if we analyze this discretization, we can see that this scheme is a Crank-Nicolson approach, which is going to be useful for our investigation because it gives us a sense of stability and also the second order convergence that is characterized by the Crank-Nicolson approach. Now we can talk about the conservation of the properties of the numerical implementation. The first of all is the conservation of mass. We have the third theorem letting U, B, and W solve the discrete system. Then we will have that the mass will remain the same over time. In order to demonstrate that, we need the following identities which we are going to be using for the following process. First of all, we take equation 27 and multiply it by the temporal average operator and the conjugate of U. Then we take the conjugate of this equation and make the inner product representation of those two equations. These equations can be extended using the identities we have before, and then we can add those two equations. Doing that, we can show that the time derivative of the mass is going to be equal to 0, and this confirms that the scheme conserves the mass of the system. Now we can talk about the conservation of energy. For that, we can use the following lemma, which gives us some useful identities for the inner product and the norms used on this system. The theorem here is that the energy is going to be conserved over time, and to demonstrate that, we can follow the following steps. First, we take equation 27, multiply it by delta t and the conjugate of u, and after some reduction of the system, using the identities, we can have the following expression. The second step is going to be taking equation 28, also apply the operator delta t, and multiply both sides by the following part. This equation, it is going to be used later. The same procedure is going to be used on equation 29, and using those two new equations and substituting them on the equation 46, we are going to have the following part. Reducing these expressions, we are going to have the following expression, and this will show that the energy will remain constant over time. Now we can talk about the conservation of momentum. For that, we have the following lemma that gives us some important definition for the demonstrations. The theorem here is again the conservation of the property, in this case momentum, that is going to be conserved on both directions. To demonstrate this, we take the inner product of the equation 27, we multiply the equation on both sides by the following parameter, and we rearrange algebraically these terms to have the final expression. We can also differentiate equation 27 with respect to x and take the inner product on both sides and also multiply by the average temporal operator and the conjugate of u, and then use the square root property of the discrete fractional operators and rearrange the terms algebraically. Subsequently, we add equation 51 and 52, multiply both sides by 2, and use the properties of the lemma to have the following expressions. These expressions can be rearranged multiplying it by other products, and then we will have the following part. Analyzing this, we will see that the last two terms are nullified using the definitions given on the lemma, and this will show that the momentum on x is going to be conserved over time. The same procedure can be implemented on the y direction, giving us the conservation of momentum on both directions. As a conclusion, we can say that the proposed numerical method successfully conserved the essential properties, including mass, energy, and momentum, and this opens us the doors for future works. For example, analyzing the convergence, stability, and consistency of the method, testing the numerical method in various scenarios to validate its effectiveness and accuracy, and also exploring potential applications and further refining the method to enhance its performance. I would like to thank you for your attention, and here I have the reference that I use for this work. Thank you again for your attention.